right. Well, it's 8th week. Is that where we are?
Yeah.
Yeah. Okay. All right. Well, here we are. Happy Monday. I'm going to go ahead and I'm going to just load up, our War and Peace giant text file, which is supposed to, the reason why we're doing this. Okay. Oh dear. Is that we want to get a sense of what two-letter combinations are common in the English language. Okay, why is my my menu's not working here? Okay, all right. Guess I'll have to navigate the menus like that. All right, we'll try this. Okay, so we're gonna load up War and Peace. We're gonna go through each letter each line, of which I think there's 66,000 lines. And for each line, we're going to look at every two letters. And when we see a particular letter combination, such as, like if there's a word English, we would say EN is the combination. We would add a 1 for that thing, and then we would go to NG, and then add 1 to that, GL, LI, IS, SH, and then H space, okay? And say that's how common a word can end with the letter H, and we do this for every single letter, I guess, set of letters in the line, and we build up our two-letter transition matrix up this way, okay? If a particular letter transition does not appear, we're going to go ahead and add 1 to every single cell, and that way none of the cells will have a 0, okay? Because if it's a 0, probabilities of 0 is going to cause us some issues. All right, so I go ahead and I do this. I can well, maybe I'll go ahead. Maybe I'll run these things, okay? Just save the files so that later on I can load them without having to reread all 66,000 lines of code. And I'm going to go ahead and produce our transition probability matrix. Here it is, colored. So this is 27 by 27, A through Z, and a space, okay? And so this is the first letter, and this is the second letter. And so we can see A followed by A is uncommon, okay? Whereas as far as A goes, the letter that most commonly follows the letter A is the letter N, followed by, it looks like, AT, and then looks like fairly common is AR, AS, and AL, okay? Which makes sense because R, S, T, L, and N are probably the most common consonants. And then, as far as vowels go, you can almost kind of see them because those rows are just darker in general, right? So A is fairly dark, E is fairly dark, I is fairly dark, and so is O. U, not so much, okay? And then, here's the letter Y, okay? As far as Y goes, the most common letters that follow Y are O, like in the word you, Y-E, probably from like yes, and then Y space, because a lot of words end it with the letter Y, okay? As far as the usage of the letter Y, you're probably more likely to end a word with the letter Y. And these are not all, it's not completely white. As far as this projector goes, it's really hard to see, but there is a little bit of shade right here, okay? But Y space is the most common, okay? T followed by H is very dark, okay? H followed by E is very dark, okay? Probably because we use the word the very often, okay? So anyway, this is one way that we are going to evaluate the likelihood of words, okay? And then the other way is that we've got kind of this lexicon, which may not be 100% accurate, okay, or certainly is not, but at least is halfway helpful, okay? Okay, so here's just a function that we can use to scramble up some letters and also use it to unscramble some letters, okay? So, so for example, one mapping, okay, is going to be this, all right? Which, here, let me, okay, somehow. My interface. Let me just blow up my text here. When we look at this code here, let me just print this out again, just so it fits the screen better. Okay, this says, I believe the letter A gets mapped to the letter V, B gets mapped to the letter X, C gets mapped to the letter M. And so let me just do, we're going to go with A, B, C. Okay. Oh, I'm sorry. I have it backwards. I guess A gets mapped to the letter W as far as, so I'm reading the thing the wrong way, okay? So ABC gets mapped to W, G, and T, okay? And then if I want to kind of demap this, then this shows us that A gets mapped to W, B gets mapped to G, and C gets mapped to T, okay? And so you can kind of try to decode WGT, and it outputs ABC, okay? So this is what we're going to do. Is we're going to as far as probabilities go, this is one function that we are going to do, and this is going to be probabilities based on the two-letter transitions. Okay. So when we take in a string, okay, so we're going to take in some letter mapping, and we're going to run the string that we need to try to decipher. Okay. So with we're going to take some kind of ciphered string, we're going to pass it through and try to decode it, and we're going to evaluate what is the probability of getting this decoded text. All right? And so what we do is I'm going to start off with a 0 for the log probability, and for each letter transition I'm going to add to that, because we're going to deal with the log probability. We're going to just add things rather than do a product. Okay? And all I'm doing is I'm going to look up in this transition probability matrix, I'm going to just look up, okay, I see the letter WG, all right? And how common is that? And I go WG, that's very uncommon, so we're going to add a very negative value here, okay? But if we see like TH, we're going to add, this is very high probability, so we're going to add a very small negative value, right? Because the log, all probabilities are between 0 and 1, so all of our log values are going to be negative, okay? And it's just that very uncommon ones will add very large negative values, and then high probability ones, we add smaller negative values, okay? So we just add kind of for every letter combination, we're going to do this. If we get to the end, we're going to have to look up kind of the thing where it's what letter ends with a space and things like that. And there's just a couple of things to kind of catch, beginning like the first letter of the line and whatnot. All right, so we can do that, and we can just kind of see, like, if I take this versus running this, we can see, how high or how low the probability is. Okay. The other part is we're going to look at the words. Okay, and we're going to say, okay, if we get a real word, all right, and so when we look at one word at a time, we call this an n-gram, or in this case, it's a 1 gram. Okay, and so I'm just using some code that this other man, Drew Conway, wrote. Okay. So we're going to take, once we've descrambled it, we're going to take kind of, parse it on the spaces. Okay. And we're going to try to look up and see if this word exists in our lexical database and if it has a corresponding probability. Okay, so we're going to do that. And so this just says, take in the 1 gram that you're looking up and look it up in the lexical database. So you're going to do lexical database, and this is basically $1 gram. Find that thing, and if it's there, return that probability. Okay, if it doesn't return it, okay, so if the lexical probability is null, or if it ends up giving us an NA, okay, we're going to return a very negative value. Okay, we don't want to say 0. Okay, if we give it 0, then we're going to get the log of 0 will be negative infinity, and it's going to break our code. Okay, so we want to just say, maybe there's a low probability that the intended word they wanted to transmit was XV7 or XVA or whatever, something that doesn't actually, is not a real word. We're going to say, there's still a low probability that that was the intended word. Okay, so here I'm going to do 1e minus 10. Now this is something that you can this is a value that you can change. You can say, I want to make nonsense words be a little bit more permissible, or you can make it even smaller to make nonsense words less permissible. So I'm going to do that, okay? And then the next part is calculate the probability of some kind of line of text, right? So we're going to take the text in our lexical database, and we're going to split the text based on at the spaces, okay? And we're going to kind of turn that into a vector by unlisting it, okay? So we split the text at the spaces, we unlist it, and then for each word in the text, we're going to use this function where it looks up the 1 gram probability of that one particular word. Okay, and we just add that up to the log probability of our current line of text. All right, so this function up here looks up, takes one word and looks it up in the dictionary, and then this one takes a string of text and looks up every word in the dictionary, okay, or in the lexigram. Is that all right? Okay, so here is our initial string. Okay, it's from Hamlet. Okay. Basis of the Lion King. Enter Hamlet, to be or not to be, that is the question, whether 'tis nobler in the mind to suffer the slings and arrows of outrageous fortune, or to take arms against a sea of troubles and by opposing end, right? So this is his famous soliloquy that starts off, to be or not to be. And so technically this is enter Hamlet, and then this thing that says ham, it just coincidentally is a word also, is in the kind of the play thing. It just says, character ham, colon, has this line of text, right? That's what's going on. I could remove it, but that's what we have here, right? Okay, and so here I'm going to just scramble this up, okay? And so this is what our text looks like, right? So here we have used our decoder key, and we get Hicks the key, right? Okay, so we can't read this, right? This is nonsense words, okay? And we would say, okay, you look at this and you go, well, maybe this is some foreign language, but probably not, right? Okay, and so what we want to do is we want to say, well, okay, what could this be, right? So what we're going to do is we are going to just start off with some initial random decoder key, right? So I have no idea what this is, but I'm going to just take 26 letters, scramble up the other 26 letters, match them up, and say this is my decoder key, okay? So right now my decoder key is just, I guess the letter L goes to, I don't know, I don't remember how this goes, okay? But the L goes to A or A goes to L, and E goes to B, I think. L goes to A, E goes to B, B goes to C, G goes to D, stuff like that, okay? And so if I apply this to this scrambled text, okay, I'm going to get back nonsense, right? So if I run this, the current decode, okay, so we can see, you know, the letter E goes to the letter B, all right, and so here it is, and then this is my translation based on my current decoder key, and I get bims as okay, and that's not, we'd say, okay, well that can't be right, all right? So we look at this and we say that can't be right. Okay, but we're gonna just run it through the kind of our two methods. One, we're gonna evaluate how likely is this to be the original message, okay? How likely is this to be the original message? And we're going to say, pretty low, okay, all right, and this is, so we're gonna say, okay, BI, okay, I guess that could happen, IN, that could happen, NB, some words, BZ, that's pretty unlikely, right, and then we have other combinations, right, VZ, ZZ, ZJ, like these are super uncommon, and so these are gonna contribute fairly high negative values to our log likelihood, okay, and then the other part is we're going to take this, split it up on the spaces, and look up and say, all right, does the word NUVN appear anywhere in your lexical dictionary? And it's going to say, nope, that does not appear. So we're going to get very negative words. Okay, let's see if any of these things might appear. Maybe NJ, I don't know. NJ could appear in there, I'm not sure. I guess I could look it up. Lexical database. Lexical database $. NJ, is that, okay, no, NJ does not appear, but maybe RI? No, wait, R? Something. Okay, let's see if RI, lexical database $RI. Okay, well, RI by itself does not appear, so we would get something. Okay, well, oh, NUB, nub, appears. Okay, so we can do this, and that gives us this value. But pretty much everything else, okay, it's going to look up BINBZ, all right, and it's going to say that doesn't appear, and so it's going to get 1 times 10 to the negative 10, okay? And so when we apply this, the current log likelihood of the text, we get another negative value of like negative 907, okay? And then, and based on these two things, we kind of have two competing ideas for like what is likely and what's unlikely. And so you have to kind of pick a weight on how you're going to combine this. So one is based on the 2-letter transition probabilities, and we're also going to take this and give it maybe like 10% or whatever. How you want to combine this, you can alter the weight, okay? Any positive value is fine, okay? So you can weight this 10%, you can weight it 500, okay? But weighting at 500 will probably cripple your decoder thing, because basically it's going to produce super high negative values until it starts finding actual words, okay? All right. So this is what we're going to do. Okay, so let me talk about, so that's how we evaluated the likelihood, all right? Let me talk a little bit about how the Metropolis algorithm actually works, right, for this thing. Okay, so far what I've described is in code how we're going to, because I think what we had earlier was we said the probability of some mapping given the text, using Bayes' rule, is probability of the text given the mapping times the prior probability of the mapping divided by the probability of the text, okay? And we said, well, this is a constant, okay, because prior to looking at the data, all mappings are equally likely. So we said that's a constant, this is a constant, and therefore we are at probability of the mapping divided by the text is proportional to probability of the text given the mapping. Okay, and this we are going to say is going to be the probability of basically the two-letter transitions, two-letter probabilities, plus the probability of real versus nonsense words. Okay, and then times some kind of lambda to kind of weight this, right? So this is where we are now. Okay. And this is basically my probability function. Okay. So my my target distribution is basically proportional to this probability of our text given our mapping. This is what we have. Okay. What do we call? Have I been calling my target distributions F? Have I been calling it that most of the time? Okay, so we'll call this F, right? All right, and then we have some kind of proposal distribution, right? What are we proposing? We have some way to propose a potential value to try out. But what am I proposing? Well, yeah, we're proposing a new mapping, okay? So what we do is we propose a new kind of decoding mapping, right? And there's all sorts of ways we could do this, right? One is we could just do a totally random decoding mapping, okay? But that would be not recommended, right? Because there's 26 factorial possible mappings, and you're just going to end up like just hopping all over the thing until you get to some new place that happens to be good, okay? So what we want to do is we want to do this in a little bit more of a controlled fashion, so we're not just arbitrarily just teleport. Like you have to just, so this is, it's a weird space, right? It's not continuous. There's 26 factorial discrete points in our mysterious space here, and then and if I just randomly just shuffle the letters every single time, I'm just basically teleporting from one location to another location. Okay, we want to do this at least to like, okay, maybe it's not continuous, but are there like adjacent ones? And so what we'll do is we're going to just propose swapping two letters in a current mapping. Okay. So we're going to propose a new decoding mapping, okay? So let's just think back to the Metropolis algorithm, right? What we do is we propose a new value, okay? And then we evaluate, we get p move is equal to min of 1 p proposed divided by p current, okay, and then maybe we move or no, okay, and we move with probability p move. Okay, so as far as proposing a new mapping goes, right now I've got my current mapping is this, and I'm going to just propose swapping two letters here. Whoops. Where's my snipping tool? Okay. Okay, so my current looks like this. All right, and then basically what I will do is my proposed is I'm going to take this and basically just swap two letters. So I'm going to just arbitrarily pick two letters. All right, so maybe I'll pick this one and this one. Okay. All right, and so, you know, currently this gets mapped to A, B, C, D, E, and this X, Y, and Z, all right? And basically, we're going to propose swapping these two, all right? So now O will get mapped to D, and G gets mapped to X. Oops, that's too fat. So we're going to put the G there and the O there. So we're going to just propose this, okay? And then basically, we're going to just kind of descramble some text, okay? And we're going to just see, you know, if I propose a new thing, if I swap G and O, okay, so I can just kind of say, okay, so my current decode looks like this. And if I swap G and O, okay, so if my mapping basically, I'm going to just say mapping 1, 2, 3, 4. Mapping 4 is going to be the letter O. And then mapping 26, 25, 24. Mapping 24 is currently O, and we're going to set this to G, right? Okay, and basically if I do that, this is what the decoded thing will look like, right? And so right now they look almost the same, except over here, all of these x's, right? NRX becomes NRD, and XLRIEX becomes DLRIED, okay? And if we had to just compare these two and we said which one looks more like an English word, we would probably say this looks a little bit more like English than this, right? XLRIEX, that seems fairly unlikely, whereas DLRIED, like, still not a real word, but this kind of looks like dried with a typo or something, right? This is like, I don't know what this person was trying to spell. Okay, and so if I, so if you remember my, the earlier probability was negative 2000. This is what I had earlier. I can run, so this is the probability. Negative 2000 corresponds to this thing. So I don't know, maybe I'll run this through here. Okay, I'll just copy this. So this becomes this, and this gets a score of basically negative 2051. Okay, and then when I run it through the new mapping, I get something else. Okay, which looks almost the same, but is different. Okay, so, you know, like pay attention to this versus this or something like that, okay? And then I'm hoping maybe this is more likely. I don't know, maybe not. Maybe my judgment is wrong. Okay, so we're gonna run this through. This is what we have. We're gonna run this probability and this thing. Okay, oh yeah, and we get improvement, okay? So this has a score of negative 1934, okay? So by swapping the G and the O, this gave us improvement in terms of our likelihood score. Does that kind of make sense? What's happening? All right, and so we're going to do this. And so according to the Metropolis algorithm, our P proposed has a higher probability than P current, right? This is the log likelihood. So it's so less negative is a higher probability. So we're going to say this has a higher probability than this one, so we're going to move in that direction, okay? So both of these are still terrible translations, okay? But this one seems a little bit better than this one, okay? And we're going to keep doing this. We're going to keep swapping letters, right? And so some other thing might propose a swap and it turns out worse. We evaluate it, it turns out worse. We're going to say, we're not going to take that one. I mean, we might. It's going to be P proposed divided by P current. We're going to use that to decide whether we're going to take it or not. But anytime we get something better, we're going to move in that direction, okay? Now, the Metropolis algorithm is not an optimization algorithm, okay? And what we're trying to do, like what the Metropolis algorithm is supposed to do is it's supposed to give you a sample that reflects the target distribution that you want, okay? The reason why it works here, even though we're not trying, what we're trying to do is we're trying to find like a high probability thing, is that the Metropolis algorithm is useful in terms of if we start off in this very low probability zone, it will help us move towards an area of high probability, okay? And I guess we can imagine there are possible other translations or decoderings that seem feasible, right? So it says like enter Hamlet, and I don't know, maybe another possibility was like enter, I don't know, Hamler or something, right? I don't know. Okay, some other thing, and I don't know if Hamlet is even a word in the thing, but maybe both of those would seem likely or something. Okay, so what this Metropolis algorithm will do is it will give us samples of areas of high probability, right? So the Metropolis algorithm, so we want a mapping of high probability okay. The Metropolis algorithm is usually used, Metropolis algorithm is usually used to produce a sample, okay? Okay, but it's also useful because you can start off in areas of very low probability and it will favor regions of higher probability. Okay, and so we're going to start with terrible mappings to basically less terrible, and we keep iterating, and eventually we'll get to a decent mapping, and then we keep going, and then finally we might get to a good mapping, right? But here's the key part. The Metropolis algorithm is great because it can start off in terrible mappings and quickly move to less terrible regions, okay? And in the beginning, our proposal is just we're going to take two letters and possibly swap them. And in the beginning, when you start off with terrible, probably a lot of these proposed swaps will be better, okay? But then as you get into good, kind of into this decent mapping, only a few possible swaps will actually be better, right? So like if you have if the mapping is almost perfect and it's just you need to swap the letter K for the letter C or something like that, okay? So basically, I don't know how many there's 26 choose 2 possible swaps, and only one out of the 26 choose 2 is a good one that will result in a favorable swap. Okay, so so towards the end, it's gonna propose swaps, but it's gonna reject most of them because most of them will be less good, and sometimes it accepts the less good ones, right? That's part of the Metropolis algorithm, but not as often, right? And so if you're almost at like the perfect zone, and there's only like 1 or 2 swaps left, okay, there's a lot of swaps that it's going to propose, and most of them it's going to reject, right? And so so this is what we're going to do when we run it, okay? So we run this. I'm going to keep track of like which thing is like our best performing decoded thing and its score, okay? And we're going to say try this in 500 iterations, and this is basically the algorithm. The proposed mapping is we're going to just take 2 letters, okay, 1 through 26. We're going to just choose 2 of them at random, and then we're going to say, okay, swap those. 2 goes to 1 and 1 goes to 2, okay? And that's going to be a proposed mapping. And then we're going to take, we're going to decode it using the proposed mapping, calculate the probability, all right? And then what we do is we're going to, this is how we, this part is if your random u is less than the probability, okay? Except it's logged, okay? So here's our random u, and we use that to decide if we do p move or p not, right? So if it's the log probabilities, p proposed divided by p current, for log probabilities, p proposed minus p current, okay? That's what this is. Proposed combined log likelihood, and this is minus the current combined log likelihood. And we're going to say if the log of your random u is less than this, then you'll accept, and if not, you don't move, right? And so if we accept, the proposed decoding becomes the current, the proposed mapping becomes the current mapping, the proposed decoding becomes the current decoding. And if not, we don't do anything, okay? So so that's what we're gonna do. And we're gonna run this, okay? So we have, this is kind of our scrambled text, and it's terrible. And so you're gonna just see, oh, and I also have it, every time it accepts, it will print out the updated decoding, okay? But the ones that it proposes and rejects, it's not going to print up on the screen. Otherwise, you're gonna get just too much stuff, okay? So you're gonna see a lot of stuff flying by in the beginning because a lot of these things that get proposed will get accepted because a lot of them are just gonna be better than the nonsense we have. But then towards the end, it's gonna slow down, all right? So are you guys ready? Maybe, I don't know, I'm really excited. I hope this works, right? I always get nervous that like, okay, maybe I did something wrong and it's not gonna work, but let's try this. Okay, so it's going, and it's proposing all sorts of stuff. And so, we started off with all sorts of things, and already it looks better, right? This is still nonsense, but this looks like it could be a foreign language because there's like a good mix of consonants and vowels, okay? And so we have risard, any, se, all right? So now we're getting like things, sans, tu, sar, zoroste, harsad, sto, eipford, t, sar. Okay, so it's still going here. So what we have is, it's supposed to be enter Hamlet, ham, to be or not to be. And we haven't gotten there yet, right? So we've got, so what we're hoping for is this will eventually become to be or not to be, okay? It seems like it's found the O. Oh, don't let me down. Okay, we've got she, ioptered, hi, sar. I wonder if did I break anything in my text? Because it worked faster earlier. nervous that I changed something. Let me look at the code that I used last year if I did anything different. Should be faster than this. Okay, let me just stop for a second, okay? Because I had better performance last time. Let me just go ahead and just try this one more time. Load this up, load that up. Okay, so I have enter Hamlet, and then we're gonna run the coding and decode this. All right, so here it goes. Starting off with nonsense. It's already got the E in position, yeah. But let's see. Oh, it lost the E. Oh, this is so sad. Okay. I promise it worked. All right, I'm going to have to go back and kind of debug my code a little bit. Wednesday, I'll make sure it's working and you guys can see it because it's fun. But right now, something didn't happen, so we'll see. All right, that's a bummer. All right, we'll see you guys then.